So I'll be talking about learning restricted Boltzmann machines, and this is based on joint work with Guy Bressler and Freddie Kohler. So this is my first time giving this talk, so please stop me anytime with questions. So what I want to do first is introduce graphical models. This is probably not new to many of you, but the way I like to think about them is that they're a rich model for defining high-dimensional distributions based on their dependent structure. Now, there are many ways to think about them, but let's start with something concrete, which is the Ising model. That's a particular case of graphical models with pairwise interactions, and we'll be spending most of the talk talking about the Ising models and variants thereof. And what it is it's a distribution on plus minus 1 to the n, so variables take values either plus 1 or minus 1. And the way that it's defined, we have these variables capital X1 through capital Xn. And when you think about some realization, little x1 through xn, what the probability that the Ising model assigns to it looks like this function. So it's an exponential of something that's like a negative energy. And the way to think about it is that there's a quadratic term, which is the quadratic form of this vector of x's on this matrix J, and a linear part, which is the inner product between this vector of x's and h's. So the interpretation is that this vector of h's are the external fields at each one of the nodes, which means they set their bias. How likely is each one to be plus 1 or minus 1? And this matrix J, it'll be symmetric throughout this talk. It describes the pairwise interactions. When there's an entry which is really positive, it means that those two variables are likely to take on the same value, either plus 1 or minus 1 together. If they have a really negative value, it means that they're likely to take on opposite signs. And if it's 0, it means they don't directly influence each other, although there can be many indirect relationships along the way. So as usual, z is the partition function, which is chosen so that this is normalized and it really is a distribution. And we're going to spend most of our time on Ising models, but of course there are many variants you can imagine. You could imagine variants still with pairwise interactions, but where you have a larger alphabet. Those would be the Potts model. You could also have higher order interactions, which involve 3-way, 4-way, or higher interactions. Those are called Markov random fields. You can even break the symmetry and have directed relations, which are no longer reciprocal, and those would be Bayes nets. Now, what'll be really important for our purposes is the conditional independence structure of graphical models. And the right language to think about this is as you would expect through a graph. So you can take the graphical model and you can define a graph in which the vertex set is the set of variables x1 through xn. And you put an edge between two variables if they have a non-zero interaction. And the key property is that this graph is the right abstraction for which things are conditionally independent. If you give me two variables, for example, xi and xj, and you condition on another set u, then xi and xj are conditionally independent if and only if all of the paths through the graph pass through the set u. And so one of the most basic questions you can ask is, if this is a rich model for modeling the types of data we have from many different sources, are there efficient algorithms for learning graphical models from samples? Now, there's been a lot of work on this. It started really with the work of Chow and Liu, who showed that there's a polynomial time algorithm when the underlying graph has a tree structure. And they give a very simple algorithm based on mutual information and finding a max weight spanning tree. And after that, Karger and Cerebro gave a generalization to graphs of bounded tree width. So for any constant tree width, these algorithms run in polynomial time. And there's an exponential dependence on whatever the tree width may be. So a really nice work of my colleague Guy Bressler, which I quite liked, was understanding what happens for bounded degree graphical models. So let's say bounded degree Ising models. So if the max degree is d, then it turns out, and this is pretty surprising, that there's an f of d times poly and n algorithm. So the f of d depends doubly exponentially on the max degree. So the running time in this algorithm is 2 to the 2 to the d times some poly and n. But the important thing is it's not an n to the d type algorithm, which you would get by brute force searching over who your neighbors are, if you didn't know anything. Now, this was improved in later work by Vouffray et al. And Clivens and Mecca, who improved the dependence on the max degree to being singly exponential. And this actually turns out to be information theoretically optimal, because you just need that many samples. And there are all kinds of other work, so this is really just a brief history of learning graphical models. There are all kinds of incomparable conditions that people have imposed, but the way to think about them is what they're really stipulating is that you can get better algorithms when there's no long-range correlations between nodes. So when nodes that are far away in a graph-theoretic sense have very little influence on each other, you can often do better than some of these algorithms. All right, so now I can transition to the main point of this talk. What I'll really be interested in is not learning graphical models when you get full observations and you see all of the different variables, but what happens in the presence of latent variables. And this turns out to have a lot of surprises, so we'll have to unwrap this question in layers. But the basic question I'll be interested in is what happens if there are unobserved or latent nodes? And this is going to really complicate our life, but it's something which is really beneficial. So first of all, it makes the problem much harder because when you only observe a subset of the variables, it means that even if the full set of observations only had pairwise interactions, when you're not observing some of the variables, all of a sudden the ones that you are can interact with each other through unobserved mechanisms. And the entire point of the talk will be digesting how complicated those mechanisms really can be. But one of the neat things is that if you can learn graphical models with latent variables, it means in a lot of settings where you don't really know that you have the full set of features on which you should be making your decisions, you can still learn something and maybe discover hidden relationships that tell you after the fact what are the pieces of the story that you're missing. So in any case, with that as the motivation, let me tell you one of the most popular latent variable models, which was popularized by Hinton and collaborators. It's called the restricted Boltzmann machine. It's really just an Ising model with some set of latent variables. In fact, the underlying graph will be bipartite. So there's a set of observed nodes, x1 through xn, and there's a set of latent nodes or hidden nodes, y1 through ym. And it's going to create roughly the same distribution that you've already seen. So if I talk about a configuration of the x's and a configuration of the y's, it'll look roughly the same. There'll be a partition function. There'll be an exponential of some negative energy term. And what is that negative energy? It has a quadratic part with this interaction matrix J, and it has this linear part with these external fields on both the x and y variables. Now it'll be bipartite because this matrix J only has interactions between x's and y's, not between x's with each other or y's with each other. This isn't really such a restriction in our results, and everything will generalize to non-bipartite settings too, but let me focus on this. So when Hinton and company introduced restricted Boltzmann machines, they did a lot of things with them. Now they had heuristics for learning them, things like the contrastive divergence approach. Now, there aren't provable guarantees for those, but that's what we're trying to remedy, is we're trying to give some algorithms with provable guarantees. But some of the neat applications that they got out of it, they could do really sophisticated things with feature extraction, with collaborative filtering, topic modeling, and most crucially, actually, they're the building blocks of deep belief networks, so very powerful unsupervised models, just by taking these restricted Boltzmann machines and layering them on top of each other. And in some way, these layers produce some kind of increasingly complicated distributional structure. Now, I'm not going to go too much into the details on that, but the first question I'm going to ask is, are there efficient algorithms for learning restricted Boltzmann machines? And as I warned you, this question is going to have a few layers. So in fact, there's going to be some complexities to this. So the first major obstacle when you talk about learning restricted Boltzmann machines or any kind of graphical model that you have unobserved nodes is that what happens when you marginalize out a node is you create much more complicated dependencies among its neighbors. So what do I mean by that? Imagine I had a really simple graphical model with just pairwise interactions. What if it even had a tree structure like this? Now, if I take the root and I marginalize it out, so even though originally they're just pairwise interactions and the leaves are conditionally independent given the root, once I remove the root from the equation, the resulting marginalized distribution on the leaves is actually going to be very complicated. So it'll have some higher order dependencies. And in particular, it won't be an Ising model necessarily and usually. Yep?
Just for clarification, by learning, you mean learning the graph structure?
Yeah, that's right. So there are some subtleties here, which is that I could mean many things for learning, and I'll get into that later. We could talk about with restricted Boltzmann machines learning some graph structure that explains them, but the graph structure won't be unique. You could also talk about learning the marginal distribution on the observed nodes. So there are a few different ways you can cast it, because in general, the graph structure of the RBM will not be uniquely defined just from the observed nodes, but that's a great question. So in particular, you don't usually get Ising models, even if you started with one and you project out a single variable. So that makes things pretty hard. So maybe the first question I should answer is, all right, if we create more sophisticated distributions by marginalizing out, what kind of distributions do we create? And actually, the answer to this is something that I introduced informally, which is the notion of a Markov random field. Actually, for our purposes, it'll be a binary Markov random field, because we'll always have a distribution on plus minus 1 to the n. And so a binary Markov random field of order r is the same type of distribution we've seen before, but the difference is what shows up in the exponent is now a polynomial of degree at most r. So in fact, you could have third or up to r order dependencies when you talk about these kinds of Markov random fields. And the folklore fact capturing the picture that I gave on the previous slide was that if you take an RBM and each of your hidden nodes has degree at most r, then in fact your distribution on the observed nodes is a Markov random field of order at most r. So you really can produce up to order r dependencies. So, one approach that we could take to trying to learn restricted Boltzmann machines is we could just learn the distribution on their observed nodes as a Markov random field. So maybe I should answer the question, how well can we learn MRFs? So are there efficient algorithms for learning MRFs? And here the answer is somewhat positive, but mostly negative. So if you talk about an order R Markov random field, then there are end of the R algorithms, and there's some hidden dependence in the constant in front of the end of the R that depends on the max degree for learning order R Markov random fields. But the real problem here is that that's actually about as good as you can hope. So in fact, under standard complexity assumptions, learning an order R Markov random field, you can't do better than n to the c times r time. So you really are stuck at this very bad dependence. And in the context of an RBM, this means you run an n to the max degree of the hidden nodes, which is just way too bad. And so if you're curious what this hardness assumption is, it's the sparse parity with noise assumption, which stipulates that learning a t-sparse parity with noise, you need n to the t time. And really what happens in these works is that they show that a t-sparse parity with noise can be implemented as an order theta of t Markov random field. So you get your hardness this way. In fact, what's even worse about the reductions is that not only does it create only, if you think about t as being a constant-wise interactions, there are actually only a constant number of hyperedges in their reduction. So these are really pessimistic things. So now I can get to the more precise formulation of the question I'm going to ask, which is not just are there algorithms for learning RBMs, but are there ones that beat this Markov random field bound? So are there algorithms that run in much better than n to the d time for learning interesting classes of restricted Boltzmann machines? And you should think about these n to the d types of things as being roughly a pretty trivial algorithm in the context of RBMs, because it's like some kind of brute force search over the neighborhood. All right, so now I can get into some of the results. So the first one is really a characterization of the representational power of bounded degree RBMs. So in fact, it turns out, so one direction I explained as the folklore fact that if you marginalize out these hidden nodes, you create an order R Markov random field. But can you create every type of order R Markov random field? So actually the surprise is that you can, that actually they're equivalent in representational power. So every binary Markov random field of order t can actually be realized as the distribution on the observed nodes of an RBM whose hidden degree is at most t. So this is an exact equivalence between what types of distributions they can represent.
If you take the degree pi, the size of the variable, so one time you have your RBM as n squared parameter,
Yeah.
you cannot generate any probability distribution of the variables, right?
Right, so in fact, it's a question also of the number of hidden units, not just the degree. So in fact, right, yeah. That's exactly right. But let me dig into that in a second when we talk about the hardness results, but that's a very good point. So what this does is it precisely characterizes the representational power of bounded degree RBMs. So to put this in context, what kinds of things were known about RBMs? So actually earlier work of Martins et al. Studied the dense RBM setting. And what they showed was that you can represent parity as long as you have things with max degree being about linear. Or more generally, you could represent any function which is a predicate that only depends on the number of ones. So here we're studying things which are sparse and much more natural in some applications. Now, actually, this statement already gives us some very strong negative results about learning. In fact, even worse, it gives us hardness of improper learning for RBMs, because just based on the same connections about why Markov random fields are hard to learn, using this equivalence between MRFs and RBMs, you immediately get that sparse parity with noise also tells you that all kinds of things in the context of RBMs are hard. So it turns out that under the same assumption, under the sparse parity with noise assumption, it's hard to learn any representation of the distribution on the observed nodes, which say gets close within total variation distance of say 1/3. So here I should clarify. So what I mean is that you can spit out not even a Markov random field that describes the observed distribution, but you can actually spit out any function which is unnormalized, which you can efficiently compute, and that will implicitly give you some density function. It's hard to find any improper representation that's within 1/3 close of the observed distribution. In fact, what's even worse, and this connects to the point that Andrea was making, in fact, this reduction not only produces a bounded degree RBM, where the degree depends on the order of the sparse parity with noise, in fact, it produces an instance in which there are only a constant number of hidden nodes. So you can think about T as being constant. You might have like a bounded degree T RBM with something like 2 to the T hidden nodes, and you get the strong lower bound that even with constant max degree and constant number of hidden nodes, RBMs are as hard as sparse parity with noise to learn. So in context, the only things that I knew about before this was the work of Bogdanov, which shows lower bounds on learning graphical models with latent variables. But the way that they do it is that they show that graphical models with latent variables can represent the uniform distribution on any given circuit. And in fact, for each gate in the circuit, they use a hidden node. So in fact, in those contexts, you're actually using a ton more hidden nodes than actually the number of observed ones, as opposed to a constant. OK, so now I can get to maybe the main point now that we've unwrapped some of the layers of what we can't hope to do for RBMs. Let's say something positive. So are there any natural and well-motivated families of RBMs that we really can learn in better than end of the D time? And actually, the answer is yes, and it's a pretty cool yes. It turns out for ferromagnetic RBMs, you really can learn them much, much faster than this end of the D bottleneck that comes from the sparse parity with noise assumption. So what does ferromagnetic mean? It means that the interaction matrix is entry-wise non-negative, and that the external fields are also entry-wise non-negative. Now, just as a bit of a historical context before I explain why this type of assumption gets around these hard lower bounds, well, ferromagneticity, if that's a word, I think it is, ferromagneticity, it plays a key role in many of the classic results in statistical physics and theoretical computer science. So it goes back quite a way. There are the famous Li-Yang theorems that in the case of ferromagnetic Ising models, they characterize where the zeros are, the complex zeros of the partition function, and that's intimately related to the existence or inexistence of phase transitions. Now, closer, within the theoretical computer science community, there's the seminal work of Jerram and Sinclair that shows how much being ferromagnetic can help you algorithmically. So it turns out that for ferromagnetic Ising models, there are efficient MCMC algorithms for sampling from them. And that's just not true in that kind of generality when you remove this ferromagneticity assumption, because you need some kinds of constraints on the underlying temperature. Now, to tell you intuitively why it's going to save us is because what goes wrong when you marginalize out nodes in an RBM is that you can create very pathological higher order dependencies. The influence of one latent node on the marginal distribution on its neighbors, well, it could be canceled out by the influence of other unobserved nodes. So they could cancel out each other's effect and only create some sort of order R dependence that you just have to guess too many nodes to ever see that there is a statistical dependence. Whereas something like being ferromagnetic means that all of the interactions are going the same direction. So they can't actually cancel each other out in these pathological ways that allow you to represent MRFs. So the main result, which I'm going to show you some of the key ingredients for the proof, is that there's a simple greedy algorithm for learning ferromagnetic RBMs. So if their max degree is D, these algorithms run in f of D times Paulian n time, f of D times n squared. And the sample complexity is even better. It's f of D times log n. And you need some sort of upper and lower bounds on the interaction strength, which is needed for identifiability. I'll go into that later. But one of the neat things is that when you learn ferromagnetic RBMs, these are exactly the types of models that you can do efficient things with. Because once you have them, you can actually sample and you can perform inference. So one of the cool things is that this actually fits really well with all of the things you'd like to do with RBMs. So using some recent results of Liu et al. Based on Barvinok's approach for deterministic approximate counting, where they showed that the Li-Yang property carries over to the induced Markov random field on the observed nodes, it turns out that we can get an efficient algorithm for performing inference on the model we've learned. Namely, if you give me some realization, we can give a p-task for estimating what the probability is that the model generated it, which is pretty cool. All right, and in fact, I won't get into this level of complication, but the things I'm saying don't really, they don't require the thing to be an RBM or to have a bipartite graph. It'll work with Ising models with latent variables in general, provided you have some condition on the diameter of the unobserved nodes. Yep.
Can you say intuitively what the ferromagnetic condition means for RBMs? Like, what kind of distributions is it? They're positively correlated, everything?
Yeah, exactly. So I'm going to dig into the structural things a little bit in it. Now, I don't have a complete answer to that question, but that's, one of the things you can think about is the structural properties that are implied by being ferromagnetic. Those do impose conditions on the distribution. So I'm going to go into a few of those in a minute, but ask me again if there's anything more I can clarify. But I don't have a full, complete answer for that.
No, I was just looking for intuition.
OK, yeah. Yeah, so that's part of the intuition is just that you can't create these pathological interactions on the induced MRF. But we'll see.
In terms of what obstacles are.
Oh, OK.
But in terms of like, what kinds of things do they
They're positively correlated, yeah.
No, but
Okay, maybe a related question is, you told us about many applications of RBM at the beginning. What are applications of the ferromagnetic?
So I don't know. I mean, that's a good question. But the ferromagnetic, so you can think about one of the original applications that they had in Hinton's survey for RBMs was thinking about a community structure as being induced. So you can think, I think he has this example in a survey about people meeting in a coffee shop, and then you think about the hidden nodes as representing the different groups. Those would exactly be positively correlated in these ways. So now it's not like all of the examples in feature extraction fit into that category, but it is actually a quite natural family in terms of some positive associations of the measure that don't have these pathological dependencies. But I think that's an interesting open question. And in fact, there are many more questions when you talk about what happens when you layer them, what kinds of sophisticated distributions can you produce in this way. All right, so let me actually dig in a little bit and then, all right, yeah. Okay.
If you take the community example, then you would take, say, two community and
Yeah.
two Ising hidden nodes from that, and
Yeah.
then put negative interaction between community 1 and member of community 2, and positive between community 1 and member of community 2. Otherwise, if you take only positive, there will be all positive here. You don't see correlation.
Okay. Yeah, okay, all right, I'm not sure, that's a good point. Let's debate slightly.
I mean, just to clarify that, you are restricting here the model class to only to have the R interaction.
Yep.
Right. So you can't get that. Sorry. So you cannot get that. I mean,
That was his point. Yeah.
No, but it's still meaningful then. You don't need to have.
Yeah, you can have positive across and even more positive with.
Yeah.
Exactly.
Yeah, so I don't, exactly. I think I side with them on this. I'm not sure. It's certainly going to restrict it. I mean, you can't have your cake and eat it too, because some of these problems are hard, unless you want to solve sparse parity with noise. OK, so in any case, let's dig into what's actually going on. And here there's a really neat connection between what's going to make the algorithms tick and some old properties in mathematical physics. So actually, there's going to be a key function which is going to play the major role in this learning algorithm. It's called the discrete influence function. So it'll be the discrete influence function at some node I. And what you do is you measure the expected spin, the expectation of xi, conditioned on some set of variables s being set to all +1. So here you're thinking about this function as it maps a subset of the nodes. And then once you pin those to be the value +1, you ask what the effect is on the bias of some other node. So this function just maps subsets to a real value. And actually, something that's going to save the day is submodularity. I wish in life that when you had to optimize something and it looked hard, it just turned out to be submodular. It doesn't always happen, but here it does. And this seems a little bit miraculous to me. I guess it depends on what community you're coming from, but it turns out that this discrete influence function is monotone and submodular, as long as the Ising model is ferromagnetic. So in fact, the fact that it's submodular ties back into old results in mathematical physics that actually predate the notion of submodularity, even though they were really about submodularity in disguise. It's something called the concavity of magnetization. Now, that's a somewhat deeper topic, and I'll get into it at the end, but let me give you a little bit of a hint of the connection, which is what I can do is I can define the average magnetization, which I look at, m is defined as 1 over n of the expectation of the sum of the spins of all of these nodes. And in fact, in the case where you are ferromagnetic, in fact, let's restrict things even further. Imagine that all of the nodes experience the same external field of H. Then this is a very well-motivated setting from the standpoint of physics, and there are a lot of classic results that are known. Some of them are pretty intuitive and are not hard to prove, like this one, that if you look at the partial derivative of the average magnetization as a function of the external field H, then as you increase H, you're going to increase the average magnetization because there's more bias pushing you to the positive spin. This is a quite easy property to prove, and it's very intuitive. This one is also intuitive, but is not so easy to prove. So in fact, the average magnetization has a law of diminishing returns, that if you look at the second derivative with respect to H, that this is actually negative. So if you look at how much increasing H is going to bias the average magnetization, that's going to diminish as you continue to increase what H is. So this is called the concavity of magnetization. It follows from a classic inequality in mathematical physics called the GHS inequality, which is stronger than the concavity of magnetization, but this is one of its main applications. And this is the hint of the connection, is that submodularity is really a property about diminishing returns, and that's intimately related to things like the concavity of magnetization. So let me take that as for given, and then I'll show you the GHS inequality later and explain why they're connected. But first, let me tell you a simple greedy algorithm now that we have this underlying submodular structure to the influence function. So it'll be just a few key ideas that are going to be assembled to give the overall algorithm. So remember that the discrete influence function being submodular was a property of an Ising model. But now what happens when you have latent variables and there are some variables that you're just not observing? So you can still define the influence function. It's just that some of the nodes you can't pin because they're unobserved and you don't see them. So if the influence function was submodular when you fully observed the entire Ising model, it'll actually still be submodular when you don't observe some of the variables too, because then you're just restricting which variables you're allowed to pin. So actually you inherit the submodularity property just from the Ising structure. Now, the other key idea, this is the main idea really underneath it, is that, all right, once we have that this influence function is monotone and submodular, how are we going to use it to learn something about the graph structure? And the key property is what ought the maximizers be? So if I fix some node I, and I look at this discrete influence function at that node I, but I can only observe some of the nodes, what node should I pin to have the most influence on the bias of that node? Well, in fact, as long as you include the 2-hop neighbors of that node, you'll have the maximum influence you can have on it. So pictorially, if I have this bipartite graph, this RBM, which I have some node I, among all of the observed nodes, which one should I pin is the 2-hop neighbors, or any subset that contains all of the 2-hop neighbors. And the intuition is that once you condition on the 2-hop neighbors, you're graph theoretically separated from all of the other observed nodes. You're conditionally independent, so you can't have an influence on the actual spin of this node at I anymore. So to say this more concretely and quantitatively, so remember that we need some sorts of upper and lower bounds on the interaction strength. So we need this notion of alpha beta non-degeneracy. This makes sense even beyond ferromagneticity, which I'm going to state it that way. It's just that if you're trying to learn the graph structure, you better impose that any non-zero value is bounded away from 0. It has absolute value at least alpha. In our case, it would be positive because we're ferromagnetic. And you also need some upper bound on all of the sum of the interactions, because if they're too large, if the external field is infinity at some node, then that node is purely deterministic, and you don't get a chance to learn who its neighbors are. So you need some alpha lower bound and beta upper bound, and you need this for identifiability of the graph structure. But once you have this, the concrete technical statement that you can make is that if you give me a node I in a subset which does not contain all of the 2-hop neighbors of I, then there's some other node that you can add to the set to make a decent amount of progress. So you can always find some node J in which the difference, how much you increase the discrete influence function, is lower bounded by this function of alpha and beta. So once you have this, now the main question is really how can we maximize the discrete influence function, because we have this idea that the 2-hop neighborhood of some node ought to be the maximizers of this monotone submodular function. So there are, of course, some classic results in approximation algorithms about maximizing monotone submodular functions. For example, there's this old result of Namehauser et al., which says that if you talk about the cardinality constrained version, so I want to find the set S of size k that maximizes some monotone submodular function, there's a 1 minus 1 over e approximation factor for it. Now, that approximation algorithm won't be directly relevant for us. We can't use it off the shelf, because what happens if we get a 1 minus 1 over e approximation to the discrete influence function? That might still miss some nodes in the 2-hop neighborhood. I don't know. But what you can do instead is, instead of actually trying to find a set of some given size, you can make it a bi-criteria problem where you compare yourself to a fixed set of given size, but you allow yourself to add more nodes. So it turns out that their analysis, if you've ever seen it, works off the shelf, and it gives you an approximation algorithm that, as long as you cheat and you allow yourself a larger size set than the thing you're benchmarking against, you can get your approximation factor to converge to 1. So what this really means is that we can run this greedy algorithm of picking out the node that has the largest influence on some given node, conditioned on what we've chosen so far. And once we keep adding those, eventually we're going to run out of nodes to add, and we're going to have a small set that contains all of the 2-hop neighbors of node I. So what this means at the end of the day is, once we've learned a small superset of the 2-hop neighbors of some node, what we can do is we can just learn the induced MRF, because now when we have some node I, we don't have to guess n to the d other possibilities of which other tuples it could belong to. We know that we've restricted down to some f of d size set. And this is where we get our algorithm. So that's how all of the pieces of the algorithm fit together. Now let me tell you at least something about this mysterious thing that I mentioned, the GHS inequality. So in fact, the way that we're going to connect to the GHS inequality is through another influence function. It'll be the smooth influence function. So instead of it taking a subset, what it's going to do is it's going to take a vector h, which is how you're going to set the external fields. So the smooth influence function takes in a vector of how you set the external fields, and you output the expectation at x sub I in the Ising model where you set the external fields to h. Now the important thing is that the smooth influence function and the discrete influence function are intimately related. In fact, you can recover the values of the discrete influence function from the smooth one. All you have to do is plug in infinity in the right places and pin some nodes to actually have the value +1. So in fact, if I think about the discrete influence function with a subset S, where I'm pinning all of those nodes to +1, how would I accomplish that? I would take the original vector of external fields, and every node that's in the set S, I would replace its value in the external field with +infinity, so that it has no choice but to be set to +1. So in fact, these two influence functions, the smooth and discrete, are very related. Actually, in retrospect, because all of this stuff happened way before the notion of submodularity, what this really is it's a multilinear extension. which is kind of cool that you can take all of our modern terminology about submodular functions and transport it back in time to what's known in mathematical physics. And now, because you asked, this is the GHS inequality. So it's kind of hard for me personally to look at this and see submodularity as popping out. But this is not supposed to be intuitive. This is the thing that implies the concavity of magnetization. But the important things to know about this is that it's proven through a really powerful technique called the random current method. And the important thing is what the heck this has to do with concavity of magnetization or the smooth influence function is the fact that each of these terms can be thought of as coming from partial derivatives of the log partition function. That's a calculation you can do, and that's also true for the smooth influence function. So what it turns out is that this GHS inequality, which took me 3 lines to even write down on a slide, well, it not only implies the concavity of magnetization that I told you, this intuitive fact about the diminishing returns of the average magnetization, it also implies something about the second derivatives of the smooth influence function. So it implies that those are also non-positive. And in fact, there are other implications. So there's something called Griffith's inequality, which is also an intuitive statement that holds for ferromagnetic Ising models, that the covariance between xi and xj is non-negative, that they can only boost each other. This is a positive association for these 2 variables. And it turns out that Griffith's inequality also implies something about the partial derivatives of the smooth influence function. It implies that they're all non-negative. So now with these things that we can assemble out of mathematical physics, the GHS inequality and Griffith's inequality, which tell us things about the partial derivatives of the smooth influence function, which is really the multilinear extension, we can get back submodularity out of it. So how do these properties imply submodularity, the thing that we cared about to begin with? Well, the answer is essentially by integrating. Here we're going from the multilinear extension back to the submodular function. So the proof is pretty simple. Let's first do the fact that the discrete influence function is monotone, and then we'll do the fact that it's submodular. So the way to think about this is that imagine you give me a set S, and now I can think about H prime as the vector of external fields, where I take H and I set all of the coordinates in S to being plus infinity. So now I can write down an integral that computes the gain in the discrete influence function, how much you get by adding in the coordinate j into the set. And you can write this down as this integral of this partial derivative, where you're now varying t, which is influencing the jth coordinate, and you're varying it from 0, what it originally was at the external field, all the way to plus infinity. And this, of course, now is non-negative just by the implication of Griffith's inequality, because the first partial derivative is non-negative. So this now implies monotonicity. That comes immediately. We can actually do submodularity the same way. It'll just be slightly more complicated because now we have 2 sets. We have S and we have T. And we do the same thing where we create these new vectors of external fields, H prime and H double prime, where we set the coordinates in S and T respectively to be plus infinity. And how are we going to show this diminishing returns property, that the marginal increase that you get when you add J to the S set is larger than the marginal increase that you get when you add it to the set T, where T contains S. You do the same exact computation. You write down the difference between the influence functions as this integral of the partial derivative of the smooth influence function. And the key property is that you can lower bound that by instead plugging in H double prime. The reason for that is because the way that I've defined H prime and H double prime, H prime is coordinate-wise at most H double prime. So in fact, when I use the fact that the second derivative is non-negative, I can actually transport this inequality into the other one without increasing it. And now the right-hand side is exactly the difference in the influence function on the set T. So this is submodularity. So it's pretty amazing to me that these old results in mathematical physics were actually statements about the multilinear extension of a submodular function, and they imply submodularity in disguise. So that's pretty cool, and that completes at least what I want to tell you about the technical proof about how we have submodularity save the day and how we use that to learn the graph-theoretic 2-hop neighborhood structure. Now, there are many open questions. Some of you have already asked me those. I don't have any answers, but let me repeat the questions. So in fact, one of the most natural technical questions, which is not answered by this work, is actually whether you can properly learn ferromagnetic RBMs. Because what we actually talked about was learning an MRF description of the observed nodes. Now you can take that MRF and back out some RBM. The catch is that you don't necessarily get a ferromagnetic one. And which would be great. If you had a ferromagnetic one, you could do things like apply Jerram-Sinclair and be able to sample from it. So that's not something that we know. Even if you're given the promise that you've learned a Markov random field that's consistent with the observed nodes of some ferromagnetic RBM, we don't know how to get back ferromagneticity. Now, there are all kinds of other questions you can ask, which is, I don't really know what kinds of distributions these produce. We know what kinds of distributions RBMs produce when they're bounded degree, and that has a precise characterization, but it's pessimistic because it contains all kinds of hard things within it. This is a case in which we can learn things. What you can do with those, whether they make sense in some situations like community modeling, I'm not sure, but that's an interesting point to debate. You can even ask questions like whether you can layer them and do something interesting and create some types of monotone distributions with a hierarchical structure. And alternatively, even if you don't like this condition of ferromagneticity, my challenge to you is give me any other condition which allows me to not be so pessimistic and allows me to actually learn RBMs. Because somehow you need to avoid the types of cancellation that allow you to embed sparse parity with noise. All right, so that's about all I wanted to say. So I'll give you the quick summary of what I hope you got out of it. So first of all, we gave a precise characterization of the types of distributions that can be represented with bounded degree RBMs, and that has a nice equivalence to MRFs. Now that allowed us to give lower bounds even for improper learning. There are cryptographic reasons why it's often hard to prove lower bounds for improper learning. That's why you need something like sparse parity with noise to do it. And then I gave you a simple greedy algorithm based on this connection between the GHS inequality and submodularity, which actually provably learned the underlying two-hop structure. So I'll end there and take any more questions you guys have. Thanks. Uh-huh.
You said that if you want to learn, so if you want to reduce from learning a sparse parity with like T hidden bits, then you need an RBM with 2 to the T hidden nodes.
Yep,
correct?
that's right.
Okay, so what if and I know that this is going to run in time n to the T.
Yeah.
So what if I actually constrain, for example, the RBM to have T hidden nodes, for example?
That's an interesting question. I don't know. That also connects, with Andrea's question too about when you have even if you talk about large degree, like degree n, it's true that you can represent any distribution you want on the observed nodes with a degree at most n RBM. But the catch is that when you talk about all distributions, you absolutely do need 2 to the n hidden nodes. So it's possible that there are other ways to constrain you that prevent this kind of nasty cancellation. It's unclear. It's 2 to the d squared for the running time.
And also, can you prove this modularity using the Fortin-Castellan sampling of the Heisenberg?
Yeah, I don't know how to prove it that way. That's an interesting question. I've never seen that proof that way, but it seems to connect at least more naturally with this like multilinear extension and then integrating back to get the submodular function, even though that's not usually the way we think about connecting submodularity and multilinearity. The other point, since you asked about the f of d, note that there is a 2 to the d lower bound because you actually need that many samples to even observe some node being, some node could be that biased anyways that you, yeah. That's right, exactly. So it's exactly the same lower bound. There is a gap here that potentially you could beat the 2 to the d squared. I have no idea about that one. So that's another open question.
There is an exponential dependency on beta also.
That's right, but that's also necessary information theoretically. It's just because the beta really shows up in the exponent anyways and how you're defining the distribution. So when in this Gibbs measure, so it becomes very skewed. I don't know. Let me take a look. That's a good question. It should be, yeah. Yep.
How does this relate to problems that you might want to solve with neural networks?
Uh,
I guess what kind of version of that? Did you run it on any data? Like, what does it give?
Or can you please answer my question first and then turn to yours?
So the question was, how does this relate to like learning with neural nets? Well, so for example, before people started taking an unsupervised tack to deep learning, deep belief nets were the predominant way that people did things. So they, at the very least, can capture some very rich structures of the types of.
Be more specific and give us some kind of intuition for the issues that you're describing and talking about, which are very interesting in their own right. How they might change the way in which we would formulate or think about a problem that deals with machine learning, which is what this conference is about.
Okay. All right. So, you know, no one believes you can learn all deep neural networks. Those can certainly encode all kinds of cryptographically hard things. So the name of the game in actually proving something algorithmic and theoretical is avoiding cryptographic hardness. Now, here you talk about cryptographic hardness, it would come from hard, sparse parity with noise distributions. When you talk about unsupervised learning, even if it's a depth 2 net, it contains things like intersections of half spaces as a very trivial special case that are actually honestly cryptographically hard. So the name of the game is finding interesting models that avoid cryptographic hardness that you can actually prove positive results about.
Okay, in the interest
Yeah.
of